Okay, my name is Irfan, and I'm doing a PhD at the Biomedical Signature Systems Group. And today I'll be talking about wearable sensors as game changers for stroke recovery. The work that I do is within a Dutch project called as the Ambition, also funded by the NWO, and then the Biomedical Signature Systems is a part of the TechMed Center. What I'll talk today is about stroke. So today we'll focus mainly on the incidence and burden of stroke, start from there, and we go by the theme or by the logo that time is brain. So the idea is that every moment after stroke, you're trying to help improve recovery. But I'm more interested in the human movement part of it. So I will look at motor impairment at stroke. So just looking at movement, not other aspects of what happens after stroke. I'll look at the specifically interested in how people move, the quality of movement. How can we use wearable sensing to improve that? And also look at the upper limb and lower limb. So the upper body and the lower body. How can we use wearables to improve sensing, to improve quality after a stroke, right? So just to give you a very brief background, there are two kinds of stroke. We have the ischemic and the hemorrhagic stroke. And in ischemic stroke, you have a blood clot that disrupts or stops the flow of blood to a certain part in the brain. And in hemorrhagic stroke, you have bleeding in a certain part of the brain. These are two different kinds of stroke. And what we see currently is that there is a huge burden of stroke at the moment. So if you look at all the global diseases put together, we have 5.2% of all loss of life due to disability is because of stroke. And if you look at Europe in particular, you have 45 billion euros people spent in 2016 on healthcare costs alone. And if you look at the non-healthcare costs, that is the cost that it took to help people recover after stroke, that money that is lost because of loss of productivity and other effects, that is also about 15 billion euros. It's quite a lot of money that has been spent in trying to help people recover after stroke. And if you look at the incidence of stroke, it's seen that there's a 25% chance that people aged 20 to 64 can get stroke. So you see the huge impact and burden of stroke at this point, and what we want to do is try to help them recover. If you look at what happens after someone has stroke in terms of motor impairment, and this is frontal plane of the brain, so it's the brain that is split from here, you have two hemispheres of the brain, right? Let's just say that's the left side and the right side. The left side is responsible for controlling the motions on the right side. So you have the contralateral hemisphere controlling everything. The opposite side, and the ipsilateral is the side that is where the limb of interest. Let's assume that there is stroke in this region. Usually what happens is there are projections, pathways that go from the motor cortex, the cortex that controls movement, and that goes down your spinal cord, crosses over to the other side. But when there's a stroke, you have an issue because there is no longer flow of information from the motor cortex. Usually what happens is the motor cortex is responsible for movement, but also fine movement, precisions. So when you're able to write or squeeze your fingers, you rely a lot on motor cortex for all kinds of movement. But when there is a hindrance to information here, some function is taken over by the ipsilateral hemisphere. Unfortunately, the ipsilateral is only able to do large movements, cross movements. So if you were to reach out to do this, when you have a stroke, you would end up doing tasks or you would end up doing movements that you are not planning to do. For example, if I have this and I want to bring this to drink, I would involuntarily do some sort of motion like this because of taking over control from the ipsilateral side, and that is something that you see in people with stroke. You have these pathways that are damaged and other pathways trying to help people overcome that. Now that results in a loss of independent joint control and also quality of movement. Now, if you look at biomechanical changes after stroke, what happens is with the issue with stroke, some of them might recover their movement patterns after stroke. Some of them might be able to do the same patterns that they did before stroke because they might be lucky with the size of the stroke, or they might recover better. And now that is what we call restitution or repair of pathways. But some people might use compensatory mechanisms. So if I find that I'm not able to do this properly, I might use my left hand to do the same thing. Or I might even use my thumb to move forward to get an object so that it's much more helpful for me, or easy for me. And that is what is called as compensation. Now, after stroke, depending on the level of severity and so on, we might have people either doing restitution or compensation, or a ratio between both. Now that will lead to changes in motor control and also task performance. And you can see that in daily life, their performance will change. And that will also change skill acquisition. Now that is what people are trying to understand now, clinically, trying to see if we can measure these differences, right? Or if we can clinically assess whether there is difference between compensation or repair, and try to understand if one is using one kind of movement or the other kind of movement. And why do you want to do that? Because you can optimize therapy. And the more that you know what is someone doing, the better that you can give them training paradigms so that they go towards a more recovered pattern. But if you look at what people do currently with in the clinic, about how do you assess movement, they use a test like this. It's a Fugel-Meyer test. It's one of the most commonly used tests. And I'm just going to give a very So if you notice here, the subject is being asked to do different tasks with their hands, with their upper limb, and then there's a physician or a clinician sitting here who makes notes, right? So Fugel-Meyer is one of the most widely used performance-based impairment index, right? They're trying to understand how good or bad is someone moving, but it's always subjective because there is a human rater in the end. And if you look at the test sheet, or the sheet that they have to score in the end, this is how it looks like. So you have them doing different tasks that you saw in the video, and for each task you have to score from 0 to 2. And you can understand it's a very small margin. It's also quite subjective. What is none, what is partial, what is full. Of course, there are good reliabilities for these tests, and it's quite widely used, but still there is the element of human present here. And also, this test is not an ideal test to really differentiate between whether there is repair happening or whether there is some sort of compensation happening. And that's why we want to move towards something called as kinematics. So that is putting sensors on the body. So when you put sensors on the body, it becomes more objective, right? So if you see in the video here, you see that these sensors are able to give a good understanding of movement in the two sides. And here it says that the left side is affected. So if I play this again, you can see that very clearly how the movement in the non-affected side is, how big it is, and on the affected side, you can see that is more trembling and so on. That's why the Stroke Recovery and Rehabilitation Roundtable, that is a group of stroke experts around the globe, they came together and they thought, okay, well, let's make a few standardized assessments people should measure, standardized things that they should look for if someone has stroke. And one of the main things that they asked to do is look at kinematics. So put sensors on someone and try to measure such that it is more objective than doing Fugel-Meyer or other kinds of tests. If you have a setup like this with sensors all over the upper body, what you can also measure is you can see differences in how they behave in the clinic or at home. The first row is what they do in the clinic. So if you put someone in the sensors, you ask them to do something in the clinic, you'll find that they use the right side, which is the good side, more than the left side, which is the affected side. But if you give them a home-like situation, you see that they start to rely more on the good side, right? And you can see these really nice differences. You can make plots. Hi.
Hello. Hey.
Hey.
Hi.
So you can make these nice plots. You can see differences between the affected and the non-affected side. And you can also really measure what is the quantity of someone's movement in the upper limb, and also what is the quality of movement. Okay. Just so you know, if you have questions, just stop me in between. Okay. Now, why do we want to measure all these things after someone has stroke? Why do we want to know the quantity or quality of movement after someone has stroke? Because that's one of the goals that we want to have in terms of quality of life after stroke. Now, this is a challenge, or this is a policymaker guide for people in Europe. And one of the rehabilitation goals is to receive appropriate level of therapy both in the hospital and following discharge. So they want to make sure that people are trained well in the hospital, but when they go home, the therapy does not stop, because after stroke, recovery is a continuous process. You're always trying to improve, and of course, time is brain, as we saw earlier. Now, what I do in my project is I try to measure the quality of movement with a stroke using a minimal sensing setup. So I want something that I can measure everything that the person is doing at home, but not use a full sensor setup like you saw in the video before, but something that is just maybe a few sensors. So assuming that I have an IMU, which is something similar to a Fitbit, and I place that one on each hand, one on the pelvis, and one on each foot. This one is to measure the upper body movement, and this is to measure how the feet move. The question that I try to ask in my PhD is, with this sensing setup, how much can I say about movement quality with someone with stroke, right? So these sensors are inertial measurement units. Inertial measurement units, I'll tell you what they are briefly. But what do we actually need to measure is we want to measure the upper limb quality and also the lower limb quality. And in the upper limb, we want to measure for some standardized assessments that people would, the clinicians tell us what we want to measure. During those, we want to measure what is the quality of movement. That's what we use the term metrics. So metrics is a term or kind of a number that tells you what is the quality of that movement being done in a very simple manner. And for the lower limb, we are more interested in gait, how does someone walk, but also how does someone's balance look like. So if they're walking, can we measure their balance during walking at home? And based on all this information, is there some sort of feedback that we can give them? Okay. Now, what are inertial measurement units? Very simply put, inertial measurement units, this is one example of a commercial device, XSense, and it has an accelerometer, a magnetometer, and gyroscope. Now the accelerometer measures accelerations, linear accelerations, and what the device actually does, it places 3 of them orthogonally so it can measure accelerations in 3D. And the same goes for gyroscope, which measures how fast is something rotating, so angular velocities, and magnetometer, and that measures the magnetic field in a given environment. Using all these systems, you can measure the movement of a certain object, the rotation of a certain object, where it is in given time. And we want to apply this on humans so that we can measure how their hands move, how their legs move. And you can see that's also quite small and it can be used in daily life. You have one of these systems already in your phones, in your Fitbits, and so on. So you know how it's easy to make it minimized. I had a question, but then I skipped it. Do you want me to do that, or just because? Okay, I'm just going to keep going. Interesting thing is that we also have some sort of an input IMUs. Okay, this is the vestibular canal in the human next to the human ear, and if you look closely, you have the utricle and the saccule, and they have fluid in them, right? It's over here, and when you walk, or when you move, the fluid, the inertia of the fluid is able to measure accelerations. So you already have an accelerometer inside you, and these circular canals, they are measuring angular velocity. So you already have some sort of a IMU inside you. We don't use this in our lab, it's just to show that we have one kind of sensor in our system. But in terms of magnetometer, we don't have, let's say, a specific organ or a system that can measure magnetic field. Actually, the research is going on if we sense magnetic fields, so we wait to see if they have something to add here, right? So we have these IMUs, and we'll use the man-made one for our projects and see how far we can get with that. The first thing I'll talk about is what we do in terms of upper limb, right? So if we put IMUs in the upper limb, what do we get in terms of quality of movement and so on? But before we can actually answer that question, we were not sure what are actually quality metrics for the upper limb. Like, what do you use to measure how good is the upper limb movement quality? Like, what number or what metric do you use? So to do that, we looked at literature. We looked at a huge set of data, and we looked at about 14,000 papers, and after removing duplicates, we had about 7,900 papers. So this is the work that I do with people from Amsterdam, so it's a combined effort. And after removing the ones that we thought does not answer a question, we came up to a final of 22 papers in which people followed people longitudinally. In other sense, they put sensors on people with stroke just after they had stroke and followed them for a few months until 6 months or later, and then they try to see if these metrics can actually say something about quality of movement, right? So what we are currently doing is we are digging into these 22 papers to see which metrics can actually say something about quality. So it's a work under progress. The other thing that we also are trying to answer is, can we detect tasks of interest in daily life? So if someone is actually wearing 3 IMUs, you can see one on this hand, one on that hand, and one on the chest, can we measure the tasks of interest? And we also have some input from the stroke recovery roundtable, and they gave us a list of tasks that might be interesting to look at, which mostly is about 2D reaching. So reaching is quite a functional task that we want to know in stroke, and the better that you can reach, the more functional tasks a person can do in daily life. And with this setup and using machine learning, the student that is able to get a really good accuracy of detecting these different tasks. So the first step is to detect these instances of when is somebody doing these tasks in daily life. The second step is, during that moment, measure the quality of that movement, right? So the first step I mentioned, we did a huge literature study of what metrics are being used for quality. We haven't done that yet, but we have a short list of what could be possible numbers or measurements that tell you something about quality. For example, we look at the distance of hand with respect to the sternum. So if you have someone whose hand-sternum distance is quite large, that means he has a large area of use. If someone has to always depend on bending his sternum to reach for something, you could say that something's wrong with his upper hand. Also, peak velocity, how fast is someone moving the upper arm when they're doing a certain task. Range of wrist motion, again, it's related to the first one. You see how far is someone's workspace is, and also again, compensatory movements of trunk during each task. So is there someone bending their trunk, or doesn't have to do that? Another interesting metric that is suggested in literature is smoothness. So smoothness is shown to have some indications for recovery, and the idea about smoothness is simply how smooth is someone moving from one point to another point. So if there is something that I have to reach for, and I do it in a very smooth manner, so that's what smoothness is, and if I do it in a trembling manner, then my smoothness will be low. And if I look at this number for smoothness, then I can say a lot about whether the person has recovered, they will be more smooth, and if he has not recovered, then he's struggling, so there's less recovery. But unfortunately, you might think that there is one formula for smoothness, but sadly, if you look in the literature, you will find that different people use different metrics to measure how smooth is someone moving. So the first question we had is, which one do we take? So that's another research project by a master's student, Bauke. What he did was he made a list of all these different smoothness metrics. He looked at the definition of what smoothness is. He looked at the function of reaching. And then he made these nice simulated velocity profiles, so fake velocity profiles. And on this, he added for different duration of tasks. So he looked at how the profile would look like for different velocities, and he added noise to this profile. And he also did, he broke the profile into 2 parts. Like if you follow the yellow, which is the final velocity profile, you can see it being discontinuous at this point. For each of these, he looked at which smoothness metric is actually the best and which tells you something about movement. That's what he's currently doing. And his next goal is to apply that to data that we have from people who are actually stroke subjects. We have this data from people in Amsterdam, and they have measured for several stroke subjects these different kind of activities, and he's going to apply those metrics on these, and we will know which one is to rely on. So that's what I have to say for the upper limb, and if I have to summarize, what do we know so far from the upper limb? That we have a summary of all metrics for quality assessment, right? So it depends on that we have a list of different metrics that we can measure, and we can also detect tasks of interest. So we can measure reaching, we can measure other tasks of interest, and when we measure quality of movement, it'll be very helpful to say something about repair or compensation. So that's something that we are currently looking at. The interesting takeaway that we had from smoothness is that smoothness, we find that the definition of smoothness depends mostly on the velocity profile that we're looking at. And what interesting thing that we found is if someone is reaching to grasp an object, or if someone reaching to just point at someone, the velocity profiles actually are different. And if the velocity profiles are different, the definition of smoothness is also different. So that's something that we're looking at, and how to define our velocity profiles best, and that's a work that we still have to start. This is for the lower limb, and we go to the upper limb. We have minimal sensing of movement by IMUs in the upper limb. Before we go into minimal sensing, the question we have is what do we measure, right? For the upper limb, it was not sure what do we measure, so we did a systematic review of literature. But for the lower limb, we have some idea about what to measure. Now, this is a setup that we have developed also in our group, Biomedical Signals and Systems. It's called the 4-shoe. It has got 4 sensors here. It has got an IMU. It has got an ultrasound sensor. Now, what you want to measure for quality of lower limb is you need to know the forces while walking. You need to know the center of mass while walking, which you can get from your 4 shoes, 4 sensor. You want to know the base of support, so how much is someone's base of support, so how big are their feet spread. And there's an interesting concept called as XCOM, which tells you how stable someone is, right? So if I look at XCOM, it's simply the center of mass along with how fast is someone walking, so those velocity and position put together. What I usually do as humans is that our XCOM is pulling us when we walk forward. And every time our XCOM is forward, we keep another step to make sure that we don't fall. We make sure that we correct for that pull by the XCOM. And if we walk faster, the XCOM will be further from the base of support. And if we walk slower, it'll be much closer. So what happens is it will result in this nice video. The green dot is the XCOM, and you can see this kind of pulling the person. And the purple line is the base of support, and you can see that it pulls the person and then goes back into the base of support, and then the center of mass of the body just follows it closely. It's really interesting because when you look at people with stroke, this is not what you see. You see something much, much different. You see that the XCOM does not even leave this line for people with severe stroke, that they walk very carefully, very slow. And you can see these really nice differences. And now this subject is going to make a turn to the left, and you can also see how the XCOM relies on one leg or the other, depending on the turn being made. You can see that it's moving more toward the left leg because they're turning to the right, to the left, and you can see how it works. But when you look at the same instance for people with stroke, you would find them relying on the good leg more than on the affected leg. You can find these really nice differences, and it's a very useful parameter, XCOM, center of mass, and also base of support. Now what we want to do with IMUs is we want to measure all that with just IMUs. But you can see that with the 4-shoe, you had a lot of sensors, but with the IMUs, you're missing most of them, right? What we want to measure in the end, we want to measure forces. We want to measure where the center of mass is, how this one moves. You can measure the forces simply by just looking at the accelerations the IMU measures, and forces just mass times acceleration, so that's okay, not a problem. The center of mass you can measure by putting an IMU next to your pelvis, and you're seeing how good the pelvis is moving. But the problem is when you want to follow your feet. Now in the earlier setup, we had an ultrasound which told you the distance between the 2 feet, so it was fine. But now if I'm going to use only the IMUs, what happens is that the feet, they start to drift after a while. This is my right foot, this is my left foot, and you can see that the right foot after a few steps is relatively stable, but the left foot after a while starts to move away because there is no information about the distance between these two. You can only tell them how fast is someone walking, but you have no information about how far these two are. That's what I'm working on at the moment. How can I improve this with just IMUs, looking at some biomechanical constraints, so that in the end, instead of using these big fat shoes, which are quite heavy, we move towards a very nice minimal sensing setup. So what do we know so far from the upper limb? We know that there are different biomechanical constructs for balance, so we can measure balance in different ways by looking at different metrics. And our sensing setup has to be ambulatory and minimal in order to be able to measure in daily life. Now, to summarize the whole presentation, we understand quality of movement, and we have to set up a few standardized tasks and metrics for that. And we also find that the metrics is dependent on the activity being done. So upper limb is different, lower limb is different. Even in the upper limb, if we're doing reaching, you have to look at some tasks, and other things also some tasks. But it's very important to look at ambulatory monitoring, so you can move therapy beyond just clinic. You don't need these huge systems to measure anymore. And finally, the question that we have to ask is, can we use feedback to influence recovery? My last slide is just the people that are involved in the project. Ambition, also sponsored by NWO, the Dutch organization, with Bert-Jan, Peter, and Jaap from the university, and Rusing, Meek, Karel, Elvin, and Gert from Amsterdam, people who give inputs about the clinical side of stroke. Hans from Erasmus, May from Ipsen, Koen from 2M, Selma from Motek, and Kim from Accent. So these last few names are from the company side, and we give a lot of inputs from what is practical in trying to apply in a market, and we work very closely with them in trying to solve these problems. And I'd like to finish by one motivational slide. If you have questions, let me know.